and 3 are more similar than 1 and 2 or 2 and 3 in a lot of scenarios, but the problem is that they might not be adjacent. This is something interesting. So, hi everyone. So, in this video, we will be looking at a technology behind GitHub's code search, which is Blackbird. And I just found this blog out, which was posted by GitHub, and they have explained a little bit about how the code search works in the backend and what all has been going into this code search. It's interesting, and there are a lot of things that they have taken care of in this, and it just gives a perspective of how these things work at such a large scale and all uh, what all things have to be taken care of, right? So if you just open any repository and if you just try to find some word, it will search for a symbol, and that symbol, the all the occurrences of that symbol will be shown here, right? So it's not just about this file or this repository. It can search across repositories when you type any query over here. So as you can see, we have a repo, then we can set a lot of parameters over here, and it will simply search this query across GitHub, across all the repositories that have been indexed on GitHub, right? So, what goes behind this? How does it work so quickly, and what has been going behind this? All of this is being taken care of, and they have, explained a little bit about this in this blog. So, what basically was the problem with GitHub? So, first of all, the thing is that whenever we talk about code search, it's different from searching strings, because in code search you need to keep track of the punctuation marks as well. If there's a slash or brackets, opening bracket, closing bracket, dot, colon, semicolon, all of these things are to be taken care of, right? So that is the reason the code search functionality is always going to be different from how we search in string. So whenever we search in string, we tend we kind of remove all of these unused or something that doesn't mean anything. We remove those things out, which is called as stemming, where we remove any spaces, any symbols or anything of that sort, which just doesn't make any sense. All of these things are removed. But with code search, that is not going to happen, right? And along with all of these things, so as we know that we need to take care of all of these symbols, one thing that comes up straight away is that we need to use regular expressions, and we need to query on the basis of these regular expressions, right? So so that was one thing. So the first thing that is important, and they also have mentioned about this, is that code search is uniquely different from general text search, because we don't want any we want to have symbols and all of those things, and we need to take care of that. And another part is GitHub scale. So these are the two things which need to be taken care of while building anything of that sort. So the scale is massive. There are millions of repositories on GitHub, and many of these repositories might have similar documents or different documents, and there might be a variety of documents present in millions of repositories. So that is the reason why they got to build this Blackbird, which is different from normal searching, right? And these are the two very important things that has to be taken care of while building Blackbird. So there are different approaches that can be implemented. So one is using grep. So grep, all of us know that grep is a Linux command where we can query regular expressions from different directories or files, right? So using grep is like the brute force approach, right? Which is the most basic, and I mean, the first thing that comes up to our mind would be grep. So implement this with GitHub. Now the scale at which GitHub works, for GitHub, as they have mentioned, it takes 96 seconds to serve a single query, right? So if it takes 96 seconds, it means that it means that the the queries that it can take per second would be 0.01. So the rate at which grep would work is 0.01 QPS, which is like not even a single query per second. And the biggest disadvantage is that while executing all of this, the machine will be occupied and nobody else can be using this machine. So all the other queries that have come up will have to wait, and it will just consume a lot of time. It will take up a lot of resources, and so grep is something that cannot be used. So what for the first thing that comes up in our mind is indexing. So indexing is something that we learn in databases, that indexing a database would allow us to break the database into meaningful chunks. And once it is broken down into meaningful chunks, we can simply traverse along those chunks itself, and it will obviously reduce the cost and reduce the time that it takes to query through the data, right? So indexing is one thing that has to be done, but how would this indexing help us in at such a great scale, right? With millions of repositories and all of those things, how this indexing will be taken care of. So with indexing, the major thing is that in what terms are we going to index? So there are different options in which we can index. So one is by repo, obviously, which is the most basic thing, that you can index by a repo, and whenever similar kind of repos will be indexed together, so that we can traverse along those repos while searching, which is one option. Along with that, we can index by the language that is being used in the code. Along with that, we can index by any symbol. So there will be symbols in the code, but uh, I mean, it also implies that we will be doing it by content, right? So content, let's say. So there are basically what they have done is, let's say we have so for every file that we put in GitHub, every file has an ID, right? So that ID is mapped to a language that is being used in it. So this is the forward index, right? So this is going to be our forward index. Okay. But and in the inverted index, as they have mentioned in the inverted index, what it will do is it will map the language to an array. In array, all of these IDs will be present, right? And this is nothing but our inverted index. So in this way, this is the very basic part of how this indexing is going to take place. So one way, the forward index that is already present is that every file ID is mapped to a language, and what we do is then we map all of these languages individually to the documents or to the files that are using that certain language, right? And the list that we have at the end, the list that is produced at the end, this list is nothing but this is called as the postings list, right? So, so this is how a basic indexing looks like. But there are many different parts by which indexing is done. One would be repo, then one would be by symbols, and there are a lot of things. So basically, indexing is more importantly done on the basis of the content that is present in a file or in a repo, rather than the type of the repo or anything of that sort. Okay. Okay, and along with that, we also need one very important index, which is the n-gram index. So, what is this n-gram index? So, basically, so n-gram is something that many people might have heard about. We also do that in NLP, where I mean, it's a very generic term. N-gram, n-gram is simply a substring of length n for any string, right? So, for example, if I have a substring, let's take an example. I have a string called as null pointer. So, if we take an n-gram of it, so n-gram, let's say if we take a trigram of it. So, for a trigram, which means you need a string of length 3, and which is a substring of null pointer. So, that would be NUL, ULL, LLP, LPT. and PTR. So these are the few these are the trigrams of null pointer. So it should be a substring and of length 3. So it will form a trigram. For a bigram, it would be NUULLLLPPTTR, and for a 4-gram index, it would be NULL and such strings of length 4. Right. So that is basically the n-gram index. So n-gram index has to be taken care of, and indexing has to be done on the basis of n-gram. Why? Because we, at the end of the day, the searching is going to be on the basis of regular expressions, and these regular expressions will have a word. Let's say I'm searching for a word called null pointer, and if I go out and search for null PTR, it will so if there is an indexing already done for every gram of it, for an n-gram of it, for a certain part of this word, then we can take that part. Let's say we go to where, so we will have to do all of these lookups in the index. So it would be 1, 2, 3, 4, 5. So 5 lookups have to be done, and with every lookup, let's say if I go to the first lookup, which is NUL, so with NUL I'll search for all the document IDs. So if indexing is already present, then I can simply go to this index NUL, and with NUL, all the document IDs that are present, I'll take those up, right? Then with ULL, I'll take all the document IDs. With LLP, I'll take all the document IDs. Then with LPT, I'll take all the document IDs, and then with PTR, I'll take all the document IDs, right? So once we receive document IDs or indexed to these specific grams, we can then apply some logic on it, apply some sorting on it, apply some double check on it at the end, and then we can return the query to the user, right? So that is why, obviously, it's not going to be as simple as that, because when we are searching for such a long data, and there is something that GitHub code search, that is Blackbird search engine uses while indexing, which is a sparse gram. So that is something different. We'll be looking at that later. But basically, this is how it is going to be. So one indexing would be based on the language, and which language the repo is using or a file is using. Along with that, another index would be ngram index, which will allow us to search through the strings, where you will perform lookups to into its grams, into its ngrams, whatever grams are being formed, whatever substrings of a string are being formed. And once we perform those lookups, if indexing is already present, we can simply get all the document IDs using that index. Let's say if you have NUL, you can get all the document IDs related to NUL. Then we combine all of these document IDs, perform some double check logic at the end, and then return it to the user. So this is one approach of how indexing has to be done. But now, if we look at this ngram index, if we look, there are multiple words of this sort. There will be multiple. Along with that, in this case, we also have to take care of a bracket or any symbol that is coming up, because it changes the context of code, right? So in this case, if we try to store these indexes, it will take up a lot of memory, right? So, so that is something which can't be done. We need to find some other approach, and that is why some other approach that they have taken up. So, as they have also mentioned here, unlike a hash map, though these indices are too big to fit in memory, so instead we build iterators for each index we need to access, and then these lazily return sorted document IDs, which can then be unionized or intersected or anything that we want, and then that can be returned to the user, right? So this is uh, big big of a scale is GitHub, and at this scale, these are very small things that have to be taken care of, which can turn out to be uh, uh, hell in the long run, right? So now, how are these 45 million repositories indexed? So there are two things about GitHub, that is content addressable hashing, something uh, which is something that GitHub uses, and another thing is how is this preformed, right? These two things have given two major decisions, and they have given rise to two major decisions that have been taken by Git. So one decision is that One decision is that the GitHub. So what GitHub does is for every file or for every content that is put onto Git, it uh, it uh, it converts it into a hash as we had discussed. So it is a git blob sha. So git blob sha is a hash formed out of content. Right. So there will be some hashing function whenever we have some content. That hash function will take up that content and then it will convert it into a git blob. So git blob SHA, and this SHA is stored in the database as well. Now, why is it stored? Because there are many files or many repos or many, like for example, very simple is the README file. A README file for many repos might be same because I mean nobody. I mean, if you initialize a Git project, if you initialize any project for that matter, it will create a README file which will be of some sort, and that README file is never updated, and it remains similar for a lot of things. It is a very simple example, but there are many such examples where the files are going to be same at the end of the day for a lot of things, and those similar files don't have to. I mean, why would they have a different identifier, right? So they all of those when are put into a hash function will give out a hash which will be similar, and then those can be pointed out to those files, right? So this is something that they have implemented, and whenever they shard it, right, whenever these things are put onto databases, the sharding is based on git blob sha, right? So that is something very important, and that creates a difference, right? So sharding is sharding is based on this hash, right? So what it basically does, so what is an advantage of sharding on the basis of Git block? So let's say we have a repository which is very popular, and if we shard according to repositories and that repository is placed on some server, so it will turn that server into a hot server because that repository is popular and everybody is trying to read out, or I mean reading or writing to that repository or making any changes to that repository. So that would create a load on one server, and all of the other servers will not be at such a high load, which would obviously, I mean, it's not the right case to server put one server into a hot mode and the others not in that kind of stress, right? So that is why what they have done is they have sharded according to the git blob hash, right? So even if there are different files in a repository, these files are stored onto different databases physically, because even if the repository is popular enough and there's a lot of read from the database for that repository, it would simply fetch this content from different servers, and the traffic will be diverted to all these different databases on different servers and not onto a single server, which will obviously prevent that server to go out. So this is one thing, and another thing by GitHub is that we need to index this git blob sha in the form of a tree, right? So why tree? Because modeling this in modeling this index as a tree is another thing that was a decision made. So why do we need to index this as a tree? Because tree obviously has an advantage that trees are easy to traverse, obviously, and with trees, so basically tree is not just a tree, it also refers to a graph. And as we have already discussed, that for a graph there will be some weight, and with that weight it will obviously allow us to traverse along the direction which is more optimized, and on some basis we need to model all of this so that we traverse in a way that is more efficient and optimizing, right? So how is this tree modeled? Now for tree, what we have taken up is delta encoding. So the tree is completely based on delta encoding. So what is delta encoding? Delta encoding is basically encoding, I mean, creating a tree on the basis of difference between the base, difference between the base and the repo that we are dealing with, and the repo that we are dealing with, right? So what it basically does is, okay, so with delta encoding, what happens is we don't keep a track of exactly what the content is present in a file or a repo. The track is kept of how different the content is from the base. So the graph which will be created will obviously not be a single connected graph. It might be some disconnected graphs on the basis of some metadata. And for those disconnected graphs, there will be a base repo, and all of the other repos that are connected to that graph, they will be placed according to the fact that how it is different from that base repo. Simple way, if we take a graph, so let's say we have a graph of this sort. So in this graph, if we see, so if one is the base repository, then two and three are placed in this graph. Along with that, a weight will be assigned to them. That weight will be based on delta encoding. And what is delta encoding? Delta encoding is how different are the base and the repo that we are dealing with. So how different is three from one, and how different is two from one? On that basis, a weight will be assigned to them. Along with that, when we look at 4, when we are trying to put in 4, 4 will be compared with 3, and on that basis, a weight will be assigned to it. So basically, when we are assigning a weight to 4, it also is in the context of 1, because 3 has been assigned a weight in context of 1. So basically, we are able to get 4, the weight of 4 in context of 1, which is something that is really helpful to us, because when we're traversing along and we are going to check along all of these files or repos, it is going to be obviously it is going to be very beneficial, right? So now let's build an index. And now let's try building an index out of this. So this is basically the architecture of how index has been built, or how they first, I mean, whenever something is post or whenever some change is happening on some content, how it takes up, how GitHub takes it up, and how is it indexed. So this is a basic architecture of that. So whenever there's a push event or anything of that sort, or any change event that occurs, it will notify it to Kafka, and then Blackbird ingest crawlers will come into action. So what these Blackbird ingest crawlers will do, they'll try to crawl across. I mean, they'll crawl across the changes, and using delta encoding, some sort of delta encoding, the similarity index is calculated, right? So let's call it a similarity index for now. That's how basically it's going to work. And first of all, a similarity index is calculated by the Blackbird ingest crawlers. Okay, and then it is sent further to the Blackbird search engine, and then sharded across many different servers. So initially, so when Blackbird had to start up, and initially they had to import and dump all of the repositories and all of the content that is already present on GitHub. They had to index all of that content. So what did they do at that time? So they had a probabilistic data structure which was based on probability. Right. So they had built a data structure which was based on probability. And how did they build this? Okay, so what they have mentioned is that they have created a graph on the basis of a probabilistic data structure, and then they take up the level order traversal of a minimum spanning tree. So we are going to mainly deep dive into all of this, because this is something very interesting of why they have taken a level order traversal of a minimum spanning tree. Right. So, first of all, to determine the optimal ingest, we need a way to tell how similar one repository is to another. So, they have a probabilistic data structure based on min-hash and hyperlog. So, a data structure based on probability, which they also called as geometric filter. And for geometric filter, it is based on two different functions. One function is the min hash, and the other is hyperlog log. Right. So these two are different functions that are that on the basis of which a geometric filter is built. And why these two functions? Because calculates two different things. So basically, min hash calculates the similarity between two things. Between two things, I mean, how similar two things are, that will be calculated by min hash, uh, and how different the two things are based on how many distinct elements many distinct elements are present in a set is calculated by hyperlog log. So basically, we get a metric of how similar two things are and how distinct elements, how many distinct elements are present in a set, and a metric of how distinct these elements are in a set. That metric is combined, and a geometric filter data structure is formed. In this data structure, for every repository or for every document or for every file, uh, there's a metric that is assigned to all of them, and on the basis of that metric, the graph is formed, right? A graph is formed on the basis of this geometric filters. Once we have a graph, things look a bit simpler because graph is something that we were trying to reach out for. Okay, so once we have a graph, now how this graph is built? For this graph, the vertices are repos, and the edges are uh, I mean, the weights that are assigned are the similarity index from the geometric filter that is obtained. So this graph has two properties. One is vertices, which is for every vertex, a repo is present, and for every edge, there's a similarity index. So we get a graph, something of this sort maybe. This is a very simple graph, but obviously a very complex data structure of this sort. And for every weight, uh, I mean, edge, there will be some weight assigned to it on the basis of that something that is calculated by the geometric filter. Right. So this is the graph that we obtained. Now, what they have mentioned is that they take up so how are they going to traverse along this? So for that, what they have done is they have taken a level order traversal of the minimum spanning tree of this graph. So we know about minimum spanning tree. What is a minimum spanning tree? Minimum spanning tree is basically uh, it is basically covering all the so minimum spanning tree is covering all the vertices with minimum sum of edges, right? So basically, what we have to do is we have to cover all the vertices that are present, 1, 2, 3, and 4, with the minimum sum of edges has to be obtained, right? Uh, so let's take another example. I'll just take this. Okay, so let's say we have this graph which consists of three nodes. So, and the weight is 10, 2, and 3. Now we need a minimum spanning tree. So what a minimum spanning tree would look like is that we need to traverse along all of these vertices. Along with that, the sum of the edges that we are traversing through should the sum at the end should be minimum possible. So in this case, we cannot go from 1 to 3 or 3 to 1 because the edge is 10, which is too large, and we have to follow this way, like 3 to 1 or 1 to 3, which will give us the sum of edges as 5, which is smaller than any other case, right? So the level order traversal, so the minimum spanning tree of this would be, so this would be the level order travel, this would be the minimum spanning tree of the graph, without the edge that was weighted as 10. Right. Now, with this, after this, they take a level order traversal. Now, let's try to understand this. So, what are these weights? So, these weights are basically the similarity index. So, if 10 is the similarity index between 1 and 3, it means that 1 and 3 have a higher similarity index, which means that 1 and 3 are more similar than 1 and 2 or 2 and 3. Right. So, what we can imply from this is that 1 and 3 are more similar than 1 and 2 or 2 and 3, right? So this implication that 1 and 3 are more similar than 1 and 2 or 2 and 3, while traversing, one very important thing is that we need to traverse along similar repositories before going to a different repository. I mean, before traversing to 2, Why not? Why not intuitively? Obviously, we are going to traverse along similar repositories before going to a different repositories, right? So in that is why whenever we take a minimum spanning tree, the edges with higher values, which means the edges with higher similarity index, are truncated, and once these are off, the edges that we get are with lower values, which means the edges that we have are those which have a lesser similarity index, and that is why we will now have a level order traversal of this. So when we do a level order traversal, obviously in this 1 and 3 will be coming up on the same level, and then we will go to 2. So that allows a more optimized way of traversal. Obviously the graphs, the repos that with the repos, the scale of repos that they have, the graph that will be formed will be huge, and that is why some approximation is obviously implemented over here, and the entire graph is not obviously traversed. Some approximation takes place, and that would further allow them to traverse along all the repositories and index them. So basically, the Blackbird ingest crawler will crawl across the changes using delta encoding, similarity index. A graph will be formed. Then, in that graph, we will be traversing along that. So the graph was formed during the initial stages itself, and traversing along the graph was a problem during the initial stage itself when all of these repositories have to be dumped. But once it is formed, you just add or delete elements, and it won't be a lot of headache, right? So once all of it is crawled, according to the similarity index, we go to different repositories. Okay, so once we get into those repositories, while we are traversing, we get into those repositories, and once we get into those repositories, what is done is crawling. So blobs that are unique to that repositories are crawled. I mean, not all blobs are crawled, obviously, because blob itself is unique. So if a file is unique, then its blob has to be unique. So blobs unique to a repo are crawled, and once these blobs are crawled, uh, what it does is it will generate some metadata out of it. This metadata will consist of symbols, then the language that has been used, and the n-grams that are being used, and all sorts of such data, right? So on the basis of this data, a document is formed, right? On the basis of this data, a document is formed. Now, this document that is formed is stored into the database, which is that is into the shards, right? So this document is now stored in shards. But now, what is this document? So this document is not obviously a file or a repo that we put in, but this document would consist of a lot of metadata like symbols, language, engrams, or the git blob SHA or anything of that sort. And all of these things are added into that document, and then it is stored in shards. The reason that it is stored in shards is discussed earlier, that we don't want to load the popular repositories with it. And now these shards take these documents and build their indices, tokenizing to construct n-gram indices based on content, symbols, path, and other useful indices. Okay, so this document which is formed consists of some data, but once this data is taken, I guess some data is not taken up here, like n-grams and all of those things. That is done by these indexer shards. Once the data is stored in shards, what they do is they will now index according to index the data with analysis on the basis of n-grams, etc. Right. So n-grams is something which is important, but there will be some other analysis as well, like analyzing the symbols, etc. So how is this indexing done? Now, what is more important is how is this index the data on the basis of n-grams? How is this done? So how are these n-grams analyzed? So basically, for the n-grams, a sweet spot that is to be considered is trigrams. So whenever we are indexing, trigrams are something that would allow us to be selective about everything. Everything, all the strings or all the data that is present. But so this was on the basis of what this conclusion was on the basis of some article which was based on Russ Cox and others have noted bigrams aren't selective enough and quadgrams take up too much space. They cause some problems at our scale. So basically, what happens is, so there are two options. Obviously, there will be a trigram or bigram or all of these things. So for bigrams, obviously, these are very small. Bigrams are very small and they would take up a lot of space. Along with that, and bigrams are obviously not selective as well because how can you make a difference by selecting only two words, two letters from a lot of data and the data that is code. So in code, there are a lot of syntax that has to be taken care of, right? So bigrams are not going to work in that. Trigrams is a sweet spot, but a problem with trigrams, right? So there's a problem with trigrams. The problem is that the problem with trigrams is that now let's say, for example, we have two words. Let's say we have a string called as for, and then we have a string called as formula. So with for and formula, now with formula, let's see what are the trigrams of it. So trigrams of a formula is for ORM, for ORM. Then you have RMU, MUL, and ULA. So these are the trigrams of formula. Now, whenever we, let's say for in query, if we go out for, let's say we query of, okay, so let's say we query formula. Let's say we query formula. Now, when we query formula, what it will do is it will so it will break this formula into its n-grams, which is trigrams. Trigrams we are considering because it is considered to be a sweet spot. So if you look at trigrams, it is for ORM, RMU, MUL, ULA. So for is something which is very commonly used in codes, and then you might have some other word like MUL, which is also used in a repository or in a file or in a repository. So what it basically will do is it will give out the document IDs of all the repositories. It will give out the document IDs of all the repositories which contains for and MUL as well. So what I'm considering now is that for is a trigram that is very common and MUL is a trigram which is very common. And in coding, obviously there will be some trigrams which are very common. But if you look at this, for and MUL might be present in a lot of scenarios, but the problem is that they might not be adjacent. This is something interesting. So for and MUL are present, may be present in a repository a lot of times, but they might not be adjacent. And if it is not adjacent, why do I need to check that file? Obviously, whenever the document IDs that are generated or document IDs that are returned to the user after querying are obviously passing through a double check before it actually goes to the user. So while double checking, if I have all those files which are for and MUL, but these words are not adjacent, why would it make sense? Right? So obviously we don't want any, so we are not going to deal with trigrams. So what they have come up with is the sparse grams. So, what are these sparse grams? So, sparse grams is something very interesting. So, in sparse grams, what they do is they don't rely on a trigram or anything of that sort. What they basically do is, let's say you have a word, they've also given an example. So, with sparse grams, they have given an example of Chester. Let's take this up from here. So, let's say we have this word Chester, where after R, this is the ending of the word. And what they do basically is for every bigram. So the first step that they do is for every bigram, a weight is assigned. A weight is assigned. That weight might be on the basis of probabilistic occurrence of this bigram or a conditional probability of h given c or e given h and all of those things. So it might be something based on probability itself, and a weight is assigned to all of these bigrams. As we can see that ch has a weight of 9, he has a weight of 6, es has a weight of 3, and so on. So for every bigram a weight is assigned, and once this weight is assigned, we take n grams out of it, but not only trigrams. What grams we take here? is something very interesting. So what they do is they traverse across the entire string, take any two bigrams, and include them in the query only if the inner weights only if each of the inner weights are strictly smaller than the ones at the boundary. Right. So this is very important. So what they do is they take any two diagrams and include them in the query only if each of the inner weights are strictly smaller than the ones at the boundary. So for example, in this scenario, if we take 9 and 7. So if we look at this 9 and 7, if we look at 9 and 7, all the inner weights inside 9 and 7 are smaller than 9 and 7. So we will take up 9 and 7, which means we have CHESTER and the end word end line, whatever. So 9 and 7 is okay, 9 and 0 is not okay, 9 and 2 is not okay, 9 and 1 is not okay, 9 and 3 is not okay, 9 and 6 will be okay because there's nothing in between. So 9 and 6 we will take up, it will be CHE. Similarly, now starting from 6 and 7 is fine because all of the weights inside it are smaller than 6 and 7, so it would be HESTER and the end word. Along with that, 6 and 0 is not okay, 6 and 2 is not okay because there's a 3 in between, 6 and 1 is not okay because there's a 3 in between, and then 6 and 3. So in this way, all of these grams are taken. So now it is not restricted to a trigram or a bigram or I mean, it won't be a bigram at all, but it is not restricted to a trigram. So these different grams are taken up. These different grams are then queried, and indexing and searching is done on based on all of these grams that will be obtained. And once we get to the search engine, searching will be based on that. The query will be separated out into all of these shards, and once we get the response from all of these shards, the response will then be compiled or merged or unionized or intersected and then given to the user. And also there will be some double check that will be occurring that will take care of the fact that some unnecessary things are not being shown to the user, right? So in this way, and also they have about the life of a query. So whenever a query, so let's for example they have taken a query slash arguments org rails lang ruby, which means someone is going to search on the basis of language, and the organization is rails. What is done here is whenever a query hits on the Blackbird query service. So once the query is hit on the Blackbird query service, uh, once the query is obtained, it parses the query is obtained. It will parse the query and rewrite it. Now, how will it rewrite? So that is also something that they have mentioned. So in this way, they will rewrite it. Now, let's analyze a little bit on this of how they have rewritten this. Right. So this is how they rewrite it. And now let's look at this. So this is about the owner details. Okay. So this is nothing but the owner of the owner of the repo. So this was something that was present in the query. Who should be the owner? So organization was something that was present in the query. So the query is this. This is basically the query. So this is basically the query that we are searching for. And now as we can see, this is the regex, the regular expression, arguments with a question mark. Then the organization is Rails and language is Ruby. So all of these things are taken care of here, right? So as you can see, language ID is 326. So there might be some ID assigned to every assigned to every language that is being used. So this is the language ID. And along with that, there's the regular expression. And some other metadata that has to be taken care of, like the repository permissions and stuff. So all of those things. Now this query is produced by the Blackbird query service. Once this query is produced by the Blackbird query service, it is sent to the Blackbird search engine, right? Now this query is sent to the Blackbird search engine. Now, once it is sent to the Blackbird search engine, it will put it down to all the shards. Once it is put it down to all the shards, so the query from here goes to Blackbird search engine and then to the shards. Okay, so now with each shard, what happens is it passes the query down again. So this is the query that is formed by each shard, and let's analyze a little bit on this. So when this query is formed, now when this query is parsed, so okay, so obviously and is the intersection of all of this, and or is the union of all of this. Now there's a formula of how this regex is translated into a series of substring queries, and that is taken up from this thing. So how this is an article by Russ Cox. So this is this formula, on the basis of this formula of how the regex, a regular expression, is converted into a query. The regular expression that we obtained, that was arguments, is converted into a query. And I mean that's what comes up from the uh, I mean that's what creates a difference with the sparse index that we had, right? So the sparse index that we had input, so while ingesting we had the sparse index, and that sparse index might have had MENT or UMENTS. If we had taken a trigram, all of these things would not have been there, right? So there are these different clauses. So one clause, one iteration is for content iteration, then you have a paths iteration, then you have a symbols iteration. So multiple iterations across multiple different metadata. So for content, we use the regular expression. Regular expression that we had input in the query will go to the content, obviously. And if there is anything else like path and all of those things, or any symbol, that iteration will also be taking place inside every shard. And once the output is obtained from every shard, the output is further merged. The output is merged and double checked and sent to the user. And sent to the user. So this is how basically this is the life of a query, basically how the query works. So this was all about how this works, and obviously it has improved their metrics in a very different way. So individual shards are on the order of 100 ms, but total response times are a bit longer due to aggregating responses. Okay, checking permissions and all. So this is the double check that is performed: aggregating responses, checking permissions, and syntax highlighting. A query ties up a single CPU core on the index server for that 100 milliseconds. So before this, it was 96 seconds for a single query, and now it is taking 100 milliseconds. So it does 640 queries per second. With the grep approach, it was 0.01 QPS, right? So with the grep approach, the QPS that we had was 0.01, but now with the new approach, the QPS that we obtain is 640 queries per second. And it is very important in this scenario because whenever this query is being executed, all of the systems are executing that query on all other queries have to wait. So obviously we need to have something that runs all of this in a quick way so as to give chance to other queries as well. So yeah, so that was all about how code search works at GitHub. Thank you.